qubit is the most fragile thing we have ever tried to compute with. A stray photon, a whisper of heat, a magnetic field from a passing elevator, and the delicate state it was holding is gone. Left alone, a good superconducting qubit stays coherent for something like 100 microseconds. A useful algorithm needs billions of operations. So the whole field runs on one question: how do you build a reliable machine out of parts that fail constantly? Classical computers solved this ages ago by copying. Store every bit 3 times, and if one flips, the other 2 outvote it. Simple, boring, effective. But quantum mechanics forbids exactly that move. You cannot copy an unknown quantum state. That's the no-cloning theorem. And worse, you cannot even look at a qubit to check on it, because measuring it collapses the very superposition you were trying to protect. The escape route is beautifully sneaky. You never ask a qubit what it is. You ask a group of qubits whether they still agree with each other. Wire in extra helper qubits whose only job is to report the parity of their neighbors, whether an even or odd number of them flipped. That answer says nothing about the data itself, so the superposition survives. But if an error sneaks in, the parity flips and the machine hears the alarm without ever seeing the secret. Scale that up and you get the surface code. A checkerboard grid where data qubits sit on the squares and measurement qubits sit between them, constantly asking their neighbors the same yes or no question, thousands of times a second. When an error strikes, it lights up a pair of these checks like a tripped alarm at 2 ends of a corridor. A decoder, running on an ordinary classical computer, reads that pattern of alarms and works out what must have gone wrong in between. Here is the price. All those helper qubits, all that redundancy, means one protected logical qubit is built out of a whole neighborhood of physical ones. Current estimates land around 1,000 physical qubits for one logical qubit that's good enough to run a serious algorithm, which sounds like a losing trade, and for decades it was. If your physical qubits are too noisy, every helper qubit you add brings in more errors than it catches, and the machine gets worse the bigger you build it. But there's a threshold. Push the physical error rate below roughly 1% per operation, and the arithmetic inverts. Below that line, every extra layer of redundancy suppresses errors faster than it creates them, and the logical error rate falls exponentially as the grid grows. In 2024, Google's Willow chip crossed that line for real. They built the same logical qubit at 3 sizes, and each time they made the grid bigger, the logical error rate roughly halved instead of growing. That's the first time a quantum computer got measurably more reliable by getting bigger. So the headline qubit count is close to meaningless on its own. A machine that breaks encryption isn't a 1,000-qubit machine. It's a million physical qubits quietly impersonating a few thousand very good ones. The real race isn't who stacks the most qubits. It's who drives the error rate furthest below that threshold, because past that point, reliability is something you can simply buy with more hardware.